The laptop has crashed, so let's see. So for the rest of the lecture, we're going to talk about recursion. We're going to talk about how we analyze recursive functions, because that's something that we haven't got to yet. And we're going to talk about sorting. And sorting is kind of where we switch from analysis to fun, and we keep the fun for the rest of the course. So let's design a recursive algorithm to sort an array of n integers. We're going to call this selection sort. Who's heard of selection sort before? Probably a bunch of you. Probably a bunch of you have implemented it. Your base case is easy. If I ever say, hey, here's a list with one thing in it, it's sorted, right? Doesn't matter if you want to sort it backwards or forwards or whatever, it's sorted. There's nothing to compare it to. The recursive case. So here's the sketch for the algorithm. We have our array, and we'll just assume integers because it makes life easy, but this is still true. All of this is still true for any type you can put a comparison on, right? You can define a comparison function on any type you want, strings, more complex objects, and this stuff is still all true. So what you're going to do is you're going to scan across the array from start to finish, and you're going to find the largest element, and you're going to keep a cursor on that element. So that's like saying what index is that element at. Now, once you're through the array, what you're going to do is just swap that largest element to the end, and swap whatever's at the end into its place. So I'm swapping 2 and 8, and now I know that the last element of my array is sorted, so I can reduce the length of the array by 1, and I can call the function again, right? And you can see that I'm going to be reducing the size of the array by 1 each time until my array is sorted, right? So what does the code for this look like? You've got an array A that's of length n. If you've got more than one thing, so this is just guarding the base case. If you've got one thing, it just does nothing, and that's fine. If you have more than one thing, you set 0, the index 0 to be the max element, right? So you've got your array of stuff. You say, here's the max, and then you say, while I'm not at the end of the array, if the thing in the position I'm at is greater than the thing at the max index position, I now track that as the max, right? So if we had 10, 2, 8, 4, 1, I'm sorry, this is boring, 14. So here I would say my max thing is the 0th element, which is 10. I go through, is 2 bigger than 10? No. Is 8 bigger than 10? No. Is 14 bigger than 10? Yes. So I update that cursor to be 0, 1, 2, 3. So now max is tracking 3. Is 14 bigger than 1? Or is 1 bigger than 14? Now you're all going to be wrong no matter how you answer, because I asked the same question, but the other way. So pretty much what I get at the end is, hey, here's the max, it's 14. I'm going to put 14 here, and I'm going to swap this to 1, right? Then I'm going to basically chop off the 14, because it's already sorted in its current and final position. And then I call selection sort on the array defined up to here, right? Hopefully you can see that. Then the next time I go through, I'm going to end up with what will I end up with? 1 will be here, right? And 10 will be here, because they are the two things that swapped, because 1 was there. And then I call the algorithm again on this portion of the array. And I keep going until I've only got one thing, right? Perhaps just a bit of intuition. What do you feel like the analysis of this algorithm is? What does it feel like it runs like? I mean, I can draw a picture, kind of make it easy. Suppose you have n things. Well, after I do one iteration, how many things do I have on the next recursive call? Yeah, minus 1, right? And then how many on the next call? Sorry, this isn't a very good picture. So this is kind of what's going to happen. Do you have any kind of feelings about what this will behave like? What sort of big O we're going to get from this?
Factorial.
N squared sounds good to me, right? Because here you're going to do n steps. You're going to scan through the whole array to find the max. Here you're going to do n minus 1. Here you're going to do n minus 2, blah, 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 blah. Once you get to 1, you're not going to do anything. We know that the sum to n from I equals 1 of I is n by n plus 1 on 2, which is of n squared, right? So we can kind of just look at this and say, oh, it feels n squared. However, there are more advanced and more tricky recursive algorithms that we might need to analyze. So let's actually show how we can formally do this. We still annotate our pseudocode like before, right? So we're being a little bit lazier now than we were last week. We're saying, I know that checking a comparison, setting a variable, I know that they're constant time functions. So I just say they're constant time, right? And I know that swapping an element is constant time, right? And here, I know that I'm going to have to go through about n things. And inside that n loop here, really, I'm doing constant work, right? Because I'm doing a check and I'm doing a variable update. So these two operations here are basically constant time, but I'm going to have to do n of them, right? So this is basically saying n times some constant c, but that's still order n. So this loop here is going to go around O of n times, and I'll just get rid of that. Do you all agree? Does that kind of make sense? Cool, okay. Now the thing that is a bit annoying is that now we have this call that calls ourselves again. How do we deal with this? Well, this big scary looking thing at the end of the slide will remind you how you work with these. These are called recurrence relations, and who remembers them? Not very many people. Okay, so this isn't too scary, but basically what we're going to do is just explain how our algorithm works in terms of the base case and the non-base case. The base case, what happens? So if I've got one element, my array's sorted, right? I do no work. I do one work, right? I just say, hey, is n bigger than 1? No, done. Do we agree that that's constant time? We better. Okay, so we're going to get constant time behavior if the input size is 1. If the input size is bigger than 1, I'm going to do linear amount of work with respect to that n, and then I'm going to have to do this thing. Amount of work on an input size of n minus 1. So it's still scary, it's still recursive. It feels kind of weird, but actually these are quite okay and easy to analyze. This is, well, this is the analysis. I would do it slightly different, and maybe I'll show you how I would do it. So I'll let you have a look at this in a sec, but maybe I'll work through it. So just looking at it, we can see that T of n is linear work plus T of n minus 1. Now what we're doing here is saying, well, T of n minus 1 must be O of n minus 1 work, right? Because the definition of T of n is doing O of n, and if n is n minus 1, you do O of n minus 1. And then you have to do another call for n minus 2. And then, so you're just summing up these expansions and expanding and expanding and expanding, and eventually you're going to get to the base case where you don't do anything. So what you can see is that n is decreasing by 1 every call, so n, n minus 1, n minus 2, all the way down, and that means there are going to be n total recursive calls. And each of those recursive calls will do, the first one will do O of n, it will do n things, the next one will do n minus 1 things, the next one will do n minus 2 things, all the way down until we do one thing, and that's the same as saying n times n plus 1 on 2, and that's n squared. The next one will do n calls. And each of those recursive calls will do, the first one will do O of n, it will do n things, the next one will do n minus 1 things, the next one will do n minus 2 things, all the way down until we do one thing, and that's the same as saying n times n plus 1 on 2, and that's n squared, all right? Now, if it was me, I would abuse notation slightly differently to this, and I'll show you what I would do. I would first write T of n equals, you can get rid of the O, for example, is one thing to make this simpler. So rewrite the recurrence relation is the first thing to do. 1 if n equals 1, O, well, yeah, that's right. O of n plus T of n minus 1. I won't finish that. And what I would do is I would start by writing, like we did up there, something like this. T of n equals, I like to write this part first. I don't know why. Just find it easier, plus n. Now, at the next step, all I'm doing is plugging n minus 1 into the recurrence I have. So I'm just expanding. So basically I'm saying, if I did T of n minus 1, what happens if we plug n minus 1 into this? Well, T of n minus 1 becomes n minus 2, right? Because it's n minus 1 is minus 2. And plus n Well, n is n minus 1 plus n minus 1, right? That's just, I've just computed, or I've just looked at what happens if I plugged in t of n minus 1 here. Now I have to put these together. So where I've got t of n minus 1 here, I write all of this stuff. And I can do that again and again until it expands, right? And that's all we did here. That's all that's going on. Back to our friend Fibonacci. You can see that this is
Fibonacci. Oh, I forgot to timer. And my status is in Bible study. It's not good. Audio stream bitrate. Why's the bitrate so low? Increasing. Hello, 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 hello. This should be good enough, I think. Is that what bitrate means?
if I ever say, hey, here's a list with one thing in it, it's sorted, right? Doesn't matter if you want to sort it backwards or forwards.
Hello? Hello? That's good enough. Oh, just yapping about. My dog is so annoying. He's barking. Is this the bad one? This is the two.
It's a mistake. So this is constant time. Checking if n is less than 2, return 1. That's constant time. You do a branch, you return. Otherwise, you're going to have to do Fibonacci on n minus 1 plus Fibonacci on n minus 2. So here's your occurrence relation. Does that make sense? Does it seem pretty intuitive on how this came out? Hopefully. These will get more comfy as well. So what happens, and this is what I was alluding to before, you start off with Fibonacci n, and that's okay, it gives you one call. But that one call generates 2, and those 2 calls generate 4, and those 4 calls generate 8, 16, 32, powers of 2, doubling all the time, right? So the number of calls is doubling at each level of the recursion tree. So the number of calls has to be less than or equal to 2 to the n, right? This algorithm is in O of 2 to the n. Let me ask you a question. Is that a type bound or not?
No. Shouldn't be a type bound.
Okay.
But type bound. Think about it. Type bound means that it should be, right? Because it's
And
binary.
that's a really nice insight. So the comment was it depends on the input. Joel, you didn't say worst case, right? Is what you're saying. You just said what happens.
That's what it is, for sure.
Very good, very good. So you should always be specifying, and usually in this course, if we don't specify, we're talking about worst case input. But yes, you're right. So is big O of 2 to the n worst case? Well, it's exponential. Is it a type bound?
Worst case type bound.
Well, it was just that, I see what you're saying. Yeah, it's a bit, we're kind of falling into a trap here of conflating a single case of n input with like n growing, right? So it's going to be 2 to the n, O anyway. But I still agree that we should be saying worst case. But nonetheless, do we think this is a type bound? That's a very, very nice insight. This tree is not symmetric. So some leaves will be one level deeper than other ones at the bottom, right? That's really nice. So do we have anybody willing to say whether they think 2 to the n is a type bound or not?
2 to the n. No, it can't be a type bound because that's just.
All right, how about this? How about you learn from my mistakes? This happened last year. Last year, we had quizzes. Now, I said something like this. Which of the following options characterizes the behavior of the given recurrence? This is the same Fibonacci recurrence you just saw. What have I got here? I've got theta n log 3n. That's something I made up, obviously. Blah, blah, blah. Big theta, 2 to the n. What does big theta imply again?
Big theta is just both sides can multiply lower and upper bound. Have the same function except different constant.
O 2 to the n, omega 2n. Now,
Yeah? No. Omega 2n
where have I
is
gotten myself
greater.
into trouble here? Does anybody see what's gone wrong?
Lower bound. Definitely lower bound. Omega.
It's not theta 2 to the n. Why is it not theta 2 to the n?
It's not theta because it could be worst case.
Actually, none of these answers are correct. None of these hold. Why? What's wrong with theta 2 to the n?
Theta 2 to the n. Lower bound. Has to be lower bound.
It's not omega 2 to the n. Yeah. This actually doesn't hold. And if you're like, I don't get it and I don't know why, well, rest assured, actually, you won't need to worry about it in this course. But the truth is that, and I haven't even put it here, and I am always forgetting my maths, but this is actually phi to the n. Where phi is the golden ratio. And the golden ratio is something like 1.61. So you need to be really careful, right? And this is even an example of me screwing up because I'm being too happy to abuse notation and not thinking straight, right? This is true. Now, what's the take-home message apart from be careful? I want to remind you, in the tutes, you had a really nice question where you proved that the base of a logarithm doesn't actually matter when you compare rates of growth in classes, right? Log 2 is the same as log 3 is the same as log 10, we don't care. Is the same true for exponentials? No, or I would have been right, right? So the fact that phi is less than 2 means that phi to the n is strictly a smaller class than 2 to the n. And so this thing is not in big theta 2 to the n, it's in big O of 2 to the n. That's not a type bound, okay? If you don't know what's going on, that's okay. Think about it a little bit. The proof of this being phi to the n is a little bit tedious. I tried to do an expansion and it doesn't work. And there are reasons for that, but we'll talk about that later. This isn't even phi, is it? It's the wrong phi. Okay. So we're going to talk now about our favorite search algorithm again, with a little twist. So I've bashed it into your heads about this. Let's find some given element in a unsorted list. What if the list was sorted? Okay, I've got search. I've got an array, size n, and I've got some element k. This is boring. I want to output whether A contains K. More realistically, you would want to return the index of that element in the container. Nonetheless, it's just a small variation. So here's an algorithm that can do this. You all know this algorithm already. It's the same as the other one. It just happens that I've got a sorted array. So I start at the start. I go all the way through the list, and I say, did I find the thing? Did I find the thing? Is this the thing? Is this the thing? And when I find the thing, I say, yes, true, I found it. If I get to the end, I say, no, it's not there. Now, we know this is linear, right? Because you get a list of n things. You have to look at them all. Worst case, right? It's not in there, worst case. You go through the whole list. There's not the thing you're looking for. Can we do better? Yeah, usually if I ask, can we do better, it means that yes, we can. Binary search, yeah, that's exactly right. So binary search is a beautiful divide and conquer algorithm, and a couple of the sorting algorithms we're going to look at are divide and conquer as well. Divide gives you a very good idea of what's happening. Because the list is sorted, the idea is as follows. Let's look at the middle element. We compute the index of the middle element of the list. So suppose here we're looking for, what, 4, right? The list is sorted. We're looking for 4. Let's look at the middle element of the list. It's 8. Because the list is sorted, that means that 4 cannot be anywhere in here, right? Because the list is sorted. It has to be smaller, right? It's smaller. It has to be on the left. So then I look in the middle again, and you might have noticed that if I've got 3, 6 elements in my list, I'm going to have to decide, I'm going to have to break a tie on what is middle, right? But that's okay. It's just implementation detail. I'm looking for 4. I've got a 5 here. So 4 cannot be here either, can it? So then I look in the middle again, and I found 4, okay? Does that feel cheaper than going through all the elements? Maybe not in this case, right? Because in this case, if I was looking for 4 and I did a linear scan, I would have found it on the second comparison. However, worst case, if you're thinking
Minimum element. Okay. 4, 7. It's 7. Let's go this one. Such right.
things not in the list, this is going to blow the pants off a linear search for any reasonably large list, okay? So the idea, and you could all implement this probably in 10 minutes if you think about it. There are a few little tricky corner cases you need to handle, but it's pretty simple. So the algorithm is basically, and this is a recursive definition of binary search, but it need not be. You have your array A, basically a lower and an upper cursor. So suppose you've got your array A. The first low and upper cursors will be the start and the end of the array. You're going to search in the middle for what you're looking for, and then you're going to make a decision on whether you look to the right or look to the left. And when you look to the left, your upper becomes this one, and you basically ignore all of this, and vice versa if you look the other way, right? So you're always chopping off half of the search space on each iteration of the algorithm. This part here is just saying, so what have we got going on here? If your upper cursor is left of your lower cursor, it means that the thing you're looking for is not in there. So if they ever cross over, this is just finding the middle. And then if the thing is bigger than the one you're looking for, you need to go to the left. Otherwise, you need to go to the right. Otherwise, you found it, and you could return true. Now, this is just one possible implementation. You might try and implement it. I would say it's worth doing. You probably remember from last week, I had an algorithm when I was talking about counting the number of strings repeating, right? That was actually using a binary search variation that was doing lower bound and upper bound binary searches. Now, the only difference from that algorithm was that it didn't halt when it found a match. It kept going until it found the lowest match or the uppermost match. Because the truth is, a list might be like 7, 7, 7, 7, 7, 8, blah, 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 6. And you might come in and you're looking for 7. You might find this 7, but for special occasions, certain algorithms, like the one I was talking about last week, you might wish to find the first 7 or the largest, largest is a bad word, the most rightmost. Sorry, that's also very bad. The furthest left and the furthest right 7s, right? And these are basically just called, if you look up lower or upper bound binary search, okay? Now, if we want to do some analysis on this thing, it's also pretty easy because if you look at the algorithm, well, doing some ifs, constant time, doing a calculation on where the middle is, constant time, doing a check is constant time of a comparison, calling ourselves, or returning, right? So it's all constant time except for the recursive calls, which means that we get this nice recurrence out, which says it's constant time if n is less than or equal to 1. Otherwise, we do constant amount of work, plus we need to divide the problem in half each time, right? Because the problem...
That's binary search?
always gets divided in half. Do we want to try and do some analysis on this? Yep, okay. So T of n equals T of n on 2.
Let me try and do it. Put that back in.
Plus, I'm just going to write 1 instead of O1. If I substitute in n over 2, I'm going to get, so what, maybe I'll use a different color if, no, I'm not going to do that because I'm worried I'll crash my tablet again. So what I'm going to do is I'm going to substitute this for the next iteration where n is actually already n on 2. So what I'm going to get, if I call this again, is n on 2 plus 1 plus 1. Now, this plus 1 is this plus 1, and this plus 1 came from calling the thing again, right? What is n on 2 on 2? N on 4, okay, so I'll just rewrite that to be nice. If I ran this again, with n on 4 as the input, what am I going to get here? N over 8 plus 1 plus 1 plus 1, right? And again, this plus 1 is the first one.
Oh, wait. Why has it become 1?
I'm worried I'll crash my tablet again. So what I'm going to do is I'm going to substitute this for the next iteration where n is actually already n on 2. So what I'm going to get, if I call this again, is n on 2 plus 1 plus 1. Now, this plus 1 is this plus 1, and this plus 1 came from calling the thing again, right?
Oh, so yeah, because there's an O1 already. Yeah, okay.
What is n on 2 on 2? N on 4, okay, so I'll just rewrite that to be nice. If I ran this again, with n on 4 as the input, what am I going to get here? N over 8 plus 1 plus 1 plus 1, right? And again, this plus 1 is the first one, this plus 1 is the second one, and this one just came about from calling the function again. Now, we need to figure out how to get this down to the base case, because the base case is constant time, and that will be nice for our analysis. So, and this is where you have to have a bit of a leap of faith. You need to be able to see a pattern emerging here. Now, what do you see vertically going on down here? You've got n on 2, n on 4, n on 8, n on 16, n on 32.
Oh, it's a square. N on 2 square. 2 square. Two squared. 2 to the n. 1 over 2 to the what? No.
64. What do those numbers sound like? Their powers of 2, right? So I could express this as n over 2 to the k.
To the k, that's right.
Plus k, right? Because here,
Plus k.
here I've got 2 to the 1. Here I've got 2 to the 2. Here I've got 2 to the 4, right? Oh, sorry, 2 to the 3. should have yelled at me. And so the number of ones that get added also go up with k. So I've got this nice recurrence here that says t of n over 2 to the k plus k. How can I get, the last thing I need to do, I want to get this back to the base case. How can I get n to be 1 here? What can I let k equal to make n, t of n over n? Because I want n over n is 1. I want t of 1. How do I get t of 1?
T of 1. Meh.
So what is it? Let k equal log what of n? Log 2 of n.
2.
Beautiful. So what I'm going to end up with here is t of n over 2 to the log 2 of n. And we know that 2 to the power of log 2 collapses to nothing because they're inverses of each other. So this is just going to be, plus, what is k again? It's log 2 of n, right? So then continuing, that means I've got t of n over n plus log 2n, which is 1 plus log 2 of n. So what is binary search? What's the complexity class of binary search? Okay, nice.
What? Oh. Yeah, that was a lot harder than I expected.
So that's through expansion. That's not the only way to do it. Some people like drawing pictures. I'll show you how. Oh, we were going to do this anyway. Some people like drawing pictures.
Wait, is it
where
even?
That's not the only way to do it. Some people like drawing class of binary pictures. List of size n. And actually, Minhao has some really nice pictures. He usually uploads them in like week 3 or 4 when you start seeing these in the tubes. They say, hey, I've got an input size of n and I do constant work. And then on the next call, I'm going to have a size of n on 2 and I'm going to do constant work. And then I'm going to have a size of n on 4, blah, blah. And then they say, okay, what's the maximum depth of this tree that I'm building? Well, it's clearly log 2 of n because I'm halving each time. And if I've got a depth of log 2 of n, and I'm doing constant work at each, well, I've got a log 2 of n algorithm, right? So that's another way to do it if you like waving your hands a bit more.
Oh, shit.
Of n, and I'm doing constant work at each, well, I've got a log 2 of n algorithm, right? So that's another way to do it if you like waving your hands a bit more.
Why? Oh. I could only be far away.
There are other doing concepts that work at each. Well, I've got a log2 event algorithm, right? So that's another way to do it if you like labeling things. There are other functions that you might want to try. You could compute powers, for example, in this way, and I'm not going to dwell on this, we'll move on to sorting. But there's actually a log n algorithm to compute powers, which is kind of neat. So you could do linear time power computations, but you can also do log n time power computations. If you want to have a go, you could try doing some analysis on this, but I'll keep going because we're going to get to some more interesting stuff now. Let's talk about sorting. We're in an algorithms and data structures course. Sorting is clearly like the bread and butter of any algorithms and data structures course. Who's written a sorting algorithm before? Who's written a good sorting algorithm before? Disheartening. Well, after today, you all have written a good one, and I know, yeah, some of you have already. So if you were asked to sort a list, how would you do it? You'd probably do something simple like bubble sort or insertion sort. Let's have a look at some of those. So I'm going to do code. Bubble sort is a classic. And we'll go docam 2, I think. All right, you're seeing my cards. Do I need a light?
I could only feel
all right, I've got a bunch of cards. I don't really know how many to use. We can have pair. So suits don't matter. Cards matter. Numbers on cards matter, but suits don't matter. Okay, I'm going to sort a very short list here. So what bubble sort says, if we look at the code, firstly we have a flag that says sorted, and we're going to loop while that thing is not. So it's a bit tricky. Until that thing is true, we're going to loop. Okay. Now we're going to start from the first element of the list to the end of the list, and we're going to compare pairs. Now, if we find
this class is so scary. For some reason, everyone's on top of their assignment. And there's 200. I could only feel far away. And Fixagram. Head of TikTok. Got a gallery on the wall. Notable. Uniform constant search. It's wait. Yeah. Why is everyone on top of this shit? It's scaring me. And no one's asking question for maths. The one that I'm scared about as well. Grape.
Find a pair that's out of order, we're going to set that flag and say, hey, the list wasn't sorted, right? And we're going to swap them. And we're going to keep going around until we've done everything. So what that...
I think she's bored of me, chat. I'm so sad.
That means is something like this. We're going to start at the start of the list, and we're going to say, I've got a 7 and a 6. Are these sorted? No. So I'm going to swap them. And now I'm going to look at these pairs, 7 and 10. Are these sorted? Okay, so then I move on to the next pair. 10 and 3, are they sorted? No, so I swap. 10 and 5, are they sorted? No, swap. So what you can see is I've bubbled 10, the biggest element, I've bubbled it up to the end of the list. That's what bubble sort gets its name from. Now, I did a swap, didn't I? I did at least one swap, didn't I? So this flag here is false. Well, I did a swap, the list wasn't sorted. Okay, so I go again. Are these things sorted? Yep. What about these? No, I did a swap, we set the flag. Are these sorted? No. These sorted? Yep. So I set the flag, I need to do another iteration, don't I? Right, let's go again. Are these sorted? No, swap them. Swap them or not? Swap. Good, good, okay. Did I swap something? Yep, so the flag's still set, I better go again. Are these sorted? Yep, are these sorted? Are these sorted? Are these sorted? I'm done. Woohoo! Okay, so let's observe something interesting. What if my input list looked like this? What would I do? Hey, are these sorted? Are these? Are these? Are these? Oh, nothing, right? How bad was that? That was about linear time, wasn't it? Because I made one pass through the list. What about where the list is ordered backwards? Or even the first example. Do you have some intuition on how long that takes? How much work did it feel like we did in the first time we sorted the list? Well, we did at least 3 or 4 linear passes, right? For a list of 5 things. So that feels n squared, doesn't it? 2 things that you can learn right now. One is that bubble sort actually sucks, it's n squared. But second is that this is called an adaptive sorting algorithm. Adaptive means that it will be better on inputs that are more sorted. Now for bubble sort, it just means that it'll run in linear time if the list is sorted, but it's very trivial to make any sorting algorithm adaptive by, before doing anything, running an algorithm that says, is this list sorted? Let's scan through it and check. As soon as you find that that's not true, run your sorting algorithm, right? So I'll make this code available too, but basically, this is another example of bubble sort where we begin with a list that looks like this, 2, 22, 2, 2, 2, 1, 3, 5, blah, blah. After the first iteration, you can see that the biggest number's been bubbled to the end of the list. After the second iteration, the second biggest number, so on, so forth, until we end with a sorted list, okay? So that's cool, that's nice. I'll come back to this and hope that the tablet doesn't die. All right, so in 2007, Barack Obama, he was at Google, and the CEO at the time was Eric Schmidt, and Eric Schmidt asked Barack Obama, hey, what's the most efficient way to sort 1,032-bit integers? Has anyone seen this video? Does anyone know what he said? So Obama says, yeah, I think the bubble sort would be the wrong way to go about it. And there's the link, if you want the receipts, they're there. And he's right, he's right. And the reason is, like I just said, it sucks. It's an n-squared sorting algorithm. If I'm telling you that n-squared sorting algorithms suck, do you think we can do better than n-squared? You bet we can, and we're going to look at that in a sec. We can actually sort in n log n time. So merge sort is the algorithm we're about to learn, and this is a thing of beauty. It's based on the divide and conquer paradigm. It's a bit similar to binary search. In a way. We're going to be using halves of the array. We're going to split the problem in half each time. Now this thing is guaranteed to be n log n. So it's not going to get worse than n log n. And this is actually as good as it gets for worst case sorting based on a comparison model. Now the comparison model just counts how many elements you compare to each other, right? It says how many, what's the worst case number of comparisons I need to make? You can't actually get better than n log n for comparison-based sorting algorithms. And next week we'll sketch out a little proof that shows why that's the case. So how does it work? Well, actually, this is super simple. And again, it's probably, well, let me tell you how many lines of Python it is, because I've got it here. My crap implementation that does stuff it shouldn't even need to do is like 20 lines of code. Okay? So it's pretty easy to implement. Basically, you're going to take a sequence, an array. You're going to take a left and a right pointer. Again, it's recursive, so we need to know where to start and finish. And what we're going to do is return a sorted list. So what we're going to do is we're going to divide the list into 2 halves, left and right. Then we're going to recursively sort each half, and then we're going to glue them back together, okay? And this looks really simple Because it is. You take an array of size n, while the pointers haven't crossed each other, you find the middle point, you call merge sort on the left half, you call merge sort on the right half, and then you merge the two together.
What the? Over my head.
Even need to do is like 20 lines of code. Okay, so it's pretty easy to implement. Basically, you're going to take a sequence, an array. You're going to take a left and a right pointer again. It's recursive, so we need to know where to start and finish. And what we're going to do is return a sorted list. So what we're going to do is we're going to divide the list into two halves, left and right. Then we're going to recursively sort each half, and then we're going to glue them back together. Okay, and this looks really simple because it is. You take an array of size n. While the pointers haven't crossed each other, you find the middle point, you call merge sort on the left half, you call merge sort on the right half, and then you merge the two together. The only complex part here is the merge. Now, the thing we need to think about here is that you've got two sorted sequences. Okay, so imagine we've got 3, 5, 8, 11, 15, and 2, 7, 8, 15, 16. What do you think? Well, actually, I've spoiled it. You can merge these two sorted lists in linear time. So let's look at how to do that. This is called a two-finger algorithm. I could actually do this with the cards, but perhaps we'll do it here first. So the idea is that you keep a cursor on the first element of each list, and you say which one's smaller, right? So 2 smaller, clearly. So you yield the 2, and then you move the cursor up, okay? And then you say what's smaller, 7 or 3? 3, right?
It's like
and then you're here, 7 or 5? 5, 7,
tape hand.
8. Say we use this one,
Okay.
8, 11, 15, 15, 16, right? Can you see how that was linear time? I just scanned through each of those lists once. I took a pass from start to finish. Here's the algorithm. If you really don't trust me, you can implement it or you can check. It looks a little bit tricky, but it's not really. It's just what I said. You're just going to merge two sorted sequences. The observation that makes this efficient is that they're pre-sorted, right? Because they're sorted, we can do a linear pass through each, always taking the smaller element out, and we're good. Okay, so how does this thing actually work? The notation in this slide is that basically you're given this list. It's very confusing, I think. I should fix this next year. You're given this list, and the arrow is what happens after, right? So this is a little bit confusing. Basically, your input list is 7294, and you want to get 2479. And the left half of each of the blocks is showing like what the input was, and after the arrow is what the output would be. So the way merge sort works, perhaps we'll go back to the document camera. Let's just take, I don't really need to contrive an example. I'll do 6 because it's nicer with. Can you see them all? It's nicer because I'm going to split them in half. Actually, it's not really going to matter. I should do 8 or 4, probably. I'll do 4. Makes life easier. So merge sort works like this. It just says, I've got 4 elements. I'm going to make 2 halves. So I split them. It says, I have got a list of 2 elements now over here. I'm going to split them in half again. Okay? Now, a single element is already sorted, is it not? Yeah?
Mm.
Okay? So I've got 2 sorted lists here. One that's a single element list 6 and one that's a single element 10. And then I'm going to merge them together in linear time with my two-finger algorithm. So 6 comes before 10. So now this is a sorted list. It was already sorted, but we didn't know that. Now let's just pretend we had this. I've got 2 elements. I'm going to split them. I've got 2 single element lists now. A single element is already sorted. Now I use my two-finger algorithm to scan through these in linear time and create a sorted list. So now I've got 2 sorted sequences of length 2. I need to do one more pass of my two-finger algorithm. What's bigger, 3 or 6? Sorry, I put 3. I should have said what's smaller. What's smaller, 5 or 6? 5, 6, 10, right? So that was merge sort. Kind of easy, right? You just keep splitting all the way down until you've got single element lists. Single element lists are already sorted, and then you do two-finger merging all the way back up until you're done, right? So let's have a look at an execution example. You've got an input here that is, so here's an 8 number example. You've got 72943861, and the little bar in the middle is just saying that's where the split's got to happen, okay? So the left split will give me 7294. I split the left split of that into 7, 2, and then of course I get 7. 7 by itself is sorted, 2 by itself is sorted. Now I need to glue these back together in sorted order, right? So I just use the merge algorithm. So I get the 2 first and then the 7. Now I'm over on this side, I do the same thing. I take a 9 and a 4, I break them down into individual lists, 9 by itself and 4 by itself. I merge them back together in a sorted order. Now I've got 2 sorted lists of length 2 each, and now I can merge those back together in linear time. 2, 4, 7, 9. So the first half of my merge sort is done. Now I need to do the second half. So I do all that work again on the second half, and now you'll see that I've got 2 sorted sequences, right? And it's just the same recursively all the way down. So how do I get these 2 sorted sequences back together to give me the final result?
Two-finger pass algorithm.
I just merge, right? I've been merging the whole time. Every time I go down, I'm splitting. Every time I come up, I'm merging. It's always the same. The merge here
Yes.
is the same as the merge here, is the same as the merge here. It's just,
Yes.
oh, damn it, sorry. It's
Yes.
just this algorithm, okay?
Yes. Yes. Yes.
And then I get my list, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry, there's no 5. Okay, so we can analyze this thing as well. It looks kind of similar to binary search, don't you think? If we look at the recurrence relation, we have...
It does look like binary search. Should I try to analyze it? Yeah, I think that's good practice. My 2K. Please give me the hit button. Not a shit button. Alright. On my own. Beat him up my way. Why so pretty? Why so lovely? Why so pretty? Why am I me? Love me, love me, love me, love me, love me. Why? Love me, love me, love me, love me. It should be something like this. Why am I
constant time if n is less than 2.
Love me, love me,
And
love
otherwise,
me,
we
love
have
me,
2
love me,
calls, right?
beat 'em
Do you see
over.
where this 2 is coming from?
Allergy.
Yeah, right, exactly. Because at the start, I'm splitting in 2, right? And I'm calling recursively. So because I'm splitting in half, I've always got a left part and a right part, so that's making 2 calls. And each of those calls is clearly operating on n over 2, right? Because I started with 4 things, and then I'm working on 2 each, and then I'm working... on 1 each. And of course, you could start with 100,000 things, and then you'd have 50,000 each, and so on and so forth. And so the depth of that tree, we know something about that, right? We actually were talking about it when we were talking about binary search. What do we know about the depth of this tree if we're splitting in half every time? How deep will this tree get? How many?
Depth. Maximum n, right? Wait, no. Half to
How
n.
many levels are there?
N over 2.
Log 2n, right?
What?
There are log 2n levels. Now, I've got log 2n levels of a tree, and each level of that tree is doing linear work, right? Because the merge is linear time, okay? Can we plug those together? Yes, of course. And we get n log n, right? So that's an n log n sorting algorithm. So here's a bit more description about that. If you let h be the height of the tree, that's going to be log n. The amount of work at some depth is of n. Even if you think about it like this, you had n elements here. You've got 2 sets of n over 2 elements here. So that's still a total of n work, right? So it's n work here, n work here, n work here, n work here. And there are log n levels. So it's n log n, okay? You can have a think about this and have a look at the slide if you're a bit hung up. We're making good time, so I'm happy. So who's heard of quicksort? Who had heard of merge sort? Who knows how merge sort works? Oh, yeah. Where have I gone wrong? Do we want another example? Do we actually? I'm happy to do another one.
No, don't.
I know you guys don't. Seriously, who thinks that they now know how merge sort works? Okay, how about I'll come back to some code and I'll give you some code for it as well. But I actually think you should try and implement it. But next I'm going to talk about quicksort. Now, quicksort, there's a few new things coming here that we need to talk about. So firstly, we're going to explain a randomized algorithm. You haven't seen a randomized algorithm yet. Who has any idea of what this could possibly mean? Any guess?
Randomized divide and conquer.
Yeah, it has some component of randomness inbuilt, right? That's exactly right. So quicksort and merge sort kind of behave similarly conceptually, but merge sort goes splitting all the way down, and then all the hard work starts when you have to start merging because you have to do all your comparisons on the way back up. Quicksort's kind of the opposite. The idea is that you have your list. So now our list is, for some reason, they're bars of varying heights. I don't know. You pick randomly. Now, you don't need to pick randomly, but we're going to teach you to pick randomly, and I'll show you why. You pick some element randomly, this one, and you say, anything smaller, I'm going to just put on the left side, right? So you go through and say, this element's bigger, I'm going to put it on the right, and it ends up here. And then you say, this one's smaller, so I'm going to put it on the left, and it ends up here. And this one's bigger, so it goes over here, right? So all I'm doing is picking some random element and putting the smaller stuff on its left and the bigger stuff on its right. The element we pick is called the pivot, okay? So the division step is picking a random element called a pivot and making 3 groups, partitioning the list into 3 groups, less than, equal to, and greater than, okay? What we then do is basically on the left-hand lower list, we call quicksort, we repeat. On the greater list, we call quicksort and repeat. And when we've got nothing left to do, when we're at the bottom, everything's sorted, we glue them all back together and we're sorted, right? So that sounded a bit hand-wavy perhaps, but you'll see how this works. So the partition in quicksort is where you do most of the hard work. And that's why I'm saying it's a bit different to merge sort. Merge sort, you do the hard work on the way back up the tree. Quicksort, you do the hard work on the way down the tree. So what we do is we take our list and some position. The position is just the index of the pivot. So in reality, in real code land or whatever, you've got a list of unsorted elements. You're going to take some random integer between 0 and n-1, right? Because they're the indexes that are in bounds in this list. So it might be the element here might be your pivot. Because it's unsorted, we don't know anything about the distribution of elements in this list. So basically, we're going to take this element as the pivot, and then we're going to go through all the other elements and say, hey, are you less than the pivot or are you greater than the pivot? And you're going to partition the list around the pivot, okay? So the way to think about this will be create 3 empty sequences, take the pivot out of your initial list, and you could put it in the equal one if you want. While your list is not empty, take out the first element. If it's less, put it in the less list. If it's greater than the pivot, put it in the greater list. Or if it's equal to the pivot, put it in the equal list. Okay, so you're building 3 lists. Then you return those 3 lists. So you can see that the partition here is going to take linear time, because all you do is say, I've got a list, pick one of the elements randomly, and then go through all the other elements comparing to that one I picked randomly and put them in a less than, equal to, or greater than list. So that's linear time. So how does this thing execute? We obviously still have to recur, like we can't just split the list and hope we're done. Perhaps I'll come back over and do another one here. So maybe I'll try 5. So, and hopefully I don't pick a bad pivot. So I'm going to be naughty and pick 5 because I know what will happen if I pick something else, and I'll show you that in a minute. So suppose 5 is my pivot, 3 is less than, 6 is greater than, 2 is less than, 10 is greater than. Now the pivot's here, right? So now over here I pick a pivot, let's just say 3. 2 will be less than, and 3, okay? Now this side's done, so I glue these back together, and I glue these back together, and then I'm over here, I have 2 pivot elements. So of course I could glue these up here, right? Because I already know that everything down on this part is less than everything over there, because I already did that in the first pivot step. So I glue them back together. Over here I say 6 is less than 10, assuming 10 was my pivot, and then I glue those back together, and then I glue those back together. So that's quicksort. Now you might be preempting where I'm going, but I'll come back to the example in a sec. Same thing, right, with the recursion tree. I won't go through this example, but take a look. Now, why are we picking a random element as the pivot? Let's take a look. Let's suppose I always pick the first element of my list as the pivot, or the last, but let's just say it's the first, it's deterministic. If I pick 2 as the pivot, what's going to happen? Well, this is greater, isn't it? And this is greater, and this is greater, and this is greater. So the pivot's sorted, but now I have to go again, right? Now if I pick 3 as the pivot, well, 5's greater, 6 is greater, 10's greater, and now I have to go again. And I've got 5 as the pivot, and I've got 6 as the pivot, and I've got 10, and now I'm sorted, I'm sorted, I'm sorted, I'm sorted. Did that feel worse than what I did before? Yeah, that's actually going to go n squared. So if you pick a bad pivot means that your computation's not getting split into about 1/4 or 3/4, worst case. You want about half-half. In a perfect world, like merge sort, you get half on the left and half on the right. In an okay case, you get 3/4 on one side and 1/4 on the other side. If you get more than 3/4 on one side and less than 1/4 on the other side, you're entering bad vibes territory, okay? So pivot selection really does matter for quicksort. So in this case, you can see, based on how we selected the pivots, and again, you can work through this example, it won't be surprising to you, but what you can see is that this side of the computation actually did more work than the right-hand side, because it went an extra level, right? So the stuff on the left part took more work than the stuff on the right part. And so the worst case running time would be that you pick a pivot, one element, question? We'll come to that. Yeah, but no. Yeah, great question. So the question was, wouldn't just always picking the first element or the last element be equally as bad as picking a random element? Not quite. So, but it's a great question. And unfortunately, we actually don't do enough rigor in this course to really explain why, but I'll give you some hand-wavy explanation. So if you pick a bad pivot, you get one element on one side and n-1 on the other side, and on the next level you get n-2 on the other side, and then n-3 and n-4, and you see me walking all the way over the stage if you're in the room, if you're watching online, sorry. No one actually wants to watch me run and walk across the room. But basically, you end up with this computation that looks like this. It's heavy one way, right? The only thing that goes down on the left is the pivot, and all the other stuff goes to the right, and that's actually going to decay to n squared. So quicksort is an n squared and O of n squared sorting algorithm. It's no better than bubble sort, the way we talk about sorting. However, this is rare. This is not super common. So let's talk a little bit about expected running time, and this is another concept, expectation. This will come up again when we talk about hashing. Expected is sort of what happens most of the time in expectation based on probability. So consider this fact that a good call to pivot will mean that less and great, like lower or greater, the two sets, they're both, like I said before, one of them will be, they're around half each. They'll be about half of n each. In some bad case, they might be like a quarter, 3/4. That's still okay. We don't want like n minus 1 in one side and 1 in the other. That's the bad case. So we have this definition of good call like this, bad call like this. Now, the cool thing about this arbitrary definition of good or bad, and this comes back to the randomization question, is that, well, because we said, oh, about 3/4 on one side and quarter on the other is good enough, that means that about half of the pivots are good pivots. About half of the possible elements in the list will give you this behavior, okay?
Don't forget this. Size of L and G are less than 3s divided by 4. S.
If you also think about it, the number
3s divided by 4.
in the list will give you this behavior, okay? Million coins and never get ahead. It happens. I don't know if it's ever happened, but it's possible, right? But the idea is that by randomizing, we might pick a bad pivot on this iteration, but we're very unlikely to pick a bad pivot on the next iteration. So hopefully that at least answers your question to some small degree. You can think about it a little bit. And so in this model, the expected running time, so again, thinking about probabilities, the expected running time of quicksort is n log n. So in that way, quicksort and merge sort just as good as each other. Now, does anybody know actually in practice what most real, well, some real heavy-duty sorting algorithms, what do they use? For example, in the C standard library, and there aren't very, well, in C, there aren't very many things implemented for you. You usually have to implement them by yourself, but there is a sorting algorithm in there. Does anybody know what it is?
It has to be quicksort, right?
It's quicksort.
Yeah, you want
So why would we implement an algorithm that could go n squared over one that we know will be n log n? So what I'm asking you is, why would we ever prefer quicksort over merge sort if we know that quicksort could be really bad, it could be n squared, probably won't be if we pick up pivot properly by randomization, but why would we prefer quicksort over merge sort?
Probability.
Memory, exactly.
Memory?
So one really cool thing, and yes, preempting my slide, is that we can do quicksort in place. What in place means is that I don't need any additional space overhead. I have constant time space addition in addition to we can do quicksort in place. What in place means is that I don't need any additional space overhead.
No additional space overhead.
I have constant time space addition in addition to the inputs I'm given. Now, why do I like that? Well, suppose I am running merge sort and I need to make a new list of merged elements, right? I might need to allocate a list of length n. What is the cost of making a list? Is it free to allocate memory of some amount n? It's not free. Right, it's not free at all. Creating memory, asking the computer, I need this chunk of memory to put stuff there, that's not free, okay? If you can do an in-place sort, it means that you don't need any extra memory, right? You might only need constant extra memory. So in-place quicksort is a really commonly implemented sorting algorithm. And in fact, last year, this was something we didn't mean to do, but we were very, very unfortunately harsh about this. In the second assignment, we had sorting benchmarks on people's code. And some people implemented very nice merge sort code, which didn't pass some of the time, empirical time measurements that we ran them against. And the reason was they were allocating too much space. And the space allocation was essentially putting a big constant on their n log n, which was breaking our test. So beware. You can do this in place in this way.
I'm involved myself. Why is it at 244p? Wait, why are my biceps so small? Keep Jimmy.
I think there's, I've got 5 more minutes, but I'll just check. So we explain how you can do in-place partitioning. Essentially, the idea is that you just keep track of 2 pointers. Again, we've been doing that a lot.
Oh, I'm obsessed with the way that you're in my head. I'm fine, I'm sorry falling for you. So darling, this is more than anything I felt before. You're everything. I didn't think I found someone who's worth the wait. All these years of my heartbreak. Mm-hmm. That I kiss E.
A lot today. You just keep moving stuff around, shuffling stuff around the pivot. Basically, just doing some bookkeeping on a list. It's a little bit tricky, but it's possible. So why in place? What benefit? No extra memory required.
Okay. I got 3 more 2-hour lectures to watch. It's great.
So I might come back to in place next week, but in the last 2 minutes, I just want to give a couple more examples to try and drive home this big omega thing. So what if I implemented, and here's actually a real case where big omega could be useful for us to talk about. What do you think about this algorithm? It's called permutation sort. Sound all right? So I take a list, I generate every permutation of that list. I generate all possible permutations of a list of n.
Generate my list. Okay. Permutations? What does that mean? Forgot. Yeah.
Elements. How many permutations of a list?
Oh, so different variations. Okay. So n choose R.
Of n elements are there? N factorial. Okay, so I make n factorial lists here, and then I go through each one of them and I say, hey, is this a sorted list or not? Sounds like a kick-ass sorting algorithm, right? No way. So I do a call to some algorithm called gen permutations. Now I haven't given you an algorithm for that. I don't know what it does, but what I do know is that it at least creates n factorial things, right? And then if I iterate over those, I check that, until I find the sorted one. The worst case behavior is that we can do is sorted in linear time. We know that, but all we know about permutations is that there are n factorial of them. We don't know, so we know that n factorial perms, but we don't know the runtime of gen permutations. So what we can say is that we know that this is at least omega n factorial times n.
Huh? What is times n?
Because the n comes from checking the list is sorted, and the omega n factorial comes from generating n factorial permutations. Again, I didn't give you an algorithm for this. So I'm saying it at least grows n factorial. It could be worse, okay? Here's another classic favorite. Who's implemented this one before? Yeah, me too. It's called BOGO sort. There's also quantum BOGO sort and BOGO sort. The idea is that while your list isn't sorted, you randomly shuffle the list and you check if the list is sorted again. Interesting case here. The worst case is unbounded because you're never guaranteed to generate the right permutation of the list if you're using randomization. The average case is theta n by n factorial. The best case is omega n. So there are some, these are different, that's new, okay? So in the last minute, let me tell you about an application where I implemented BOGO sort for real.
What?
1 minute, guys, 1 minute, trust me. Come on, 1 minute. 1 minute for our friend BOGO sort. So in my research, I work on search engines, so algorithms on making text search over large data possible. So like if you Google search and you wonder how it comes back in 5 milliseconds or whatever, that wasn't me, that was people in the 90s, but I still work on that type of stuff. So inside the search algorithm, one of them at least, it involves a really large amount of sort calls to very short lists. So you get like 2-element lists, 3-element lists, 4-element lists, and you need to sort them. And you call sort lots and lots and lots and lots and lots. Now, I implemented BOGO sort, bubble sort, which is our, so BOGO is our like unbounded, right? Bubble is O n squared. And standard sort uses probably a combination of things, but we could just say it's n log n, for example. Now, what you see, interestingly, is that our friend bubble sort, which I've been saying sucks this whole time, it's doing just as well as C++'s standard inbuilt sort function. Why is that the case? Why? Yeah, that's a really nice insight. So one insight here is that standard sort probably has like 5 different sorting algorithms inbuilt, and it looks and says, if the list is shorter than this, use this one. If the list is between this size and this size, use this other one. If the list is bigger than this, use this one. Yep. Yeah, I'm measuring time here. Let me give you another hint. What's on the x-axis? List length. Yep. Yeah, how bad could n squared be on a list of length 5? Can't be that bad, right? So n squared algorithms on small lists, it's fine, right? So that's not super surprising. Unbounded randomized BOGO sort becomes really bad, right? Even for a list of length 5, you're orders of magnitude slower, okay? So this is another example where in the real world, if you have a problem and you know the size is very small, you can implement an n squared algorithm. It would have taken you, well, to be fair, longer than it would have taken you to call the standard sort algorithm, but it would be easy to implement. I sometimes get list lengths up to around 30. Now, clearly bubble sort for 30 is going to start being worse than probably standard sort. And I might perhaps use bubble sort for lists up to length 6 or 7, okay? All right, we made it. Thank you all.
Okay, I need to do this one as well. Oh my god. My dog is a dickhead. Oh shit. Brain running for too long.
Hey everyone. Hello, welcome back. Can you hear me at the back? Yep, thank you. All right, welcome to week 3, I think. The semester's flying by, so I'll start on some housekeeping while people settle in. Where should we start? So, a couple of questions this week in the tutes about things like how do you know that this is some mathematical truth? We obviously don't teach you every mathematical truth in this course. Sometimes we assume you know stuff from before. Maybe you learned it in like high school, maybe really early in high school, maybe you forgot. So again, I keep hitting people over the head with this. This is on the LMS, it's available, it has all the stuff you need. I would recommend getting used to it because the exam might potentially have this sheet attached to it and you might want to understand what the things on the sheet mean so you can apply them in the exam, all right? Just as an example. And this, hopefully you can see okay, has stuff like properties of logarithms. There's some stuff you probably don't need, but there's some combinatorics. On the back there are some summations, some manipulations, some properties of asymptotic analysis. You probably don't need all these, but some of you might use some of them, and so it's okay, these are in your toolkit if you need them, but I'm just saying, get the cheat sheet, right? It should be beneficial. At least get familiar with it, right? So here's my housekeeping. Okay, let's talk first about Ripple. Ripple 1's done. This week you're moderating. If you haven't done your moderation, do that, please. Easy. Some of you, it's going to take 2 weeks. So if you haven't read it, you better read it by the end of today or tomorrow, or you're putting yourself at risk, okay? I'm warning you now. We're here to help. There's going to be an assignment help session tomorrow. It runs from 2 to 4 p.m. I've put where it runs on the LMS in an announcement. So we're here to help. If you're stuck and you say, I don't even know how to get started on this thing, we can help you. We're here to help. We want to help you. We want you to have fun with algorithms. That would be the goal I have in this course is for everyone to leave and say, oh, that was kind of cool. That was kind of fun, right? But we do have to assess you. So if you're having trouble even getting started, come and see me. I've got office hours straight after this, 4 to 5 on Thursdays. We have assignment help sessions, like I said, tomorrow, 2 to 4. We have another assignment help session next week in the lecture. I booked a lecture for 3 hours. Doesn't mean you have to stay for 3 hours. Next week I'm going to do a 2-hour lecture, and then some tutors will arrive. I'll stay here, and for the last hour we'll help people debug or get started. But please, please, at least read the spec, get the code, and start thinking about it now, okay? And not now, I mean after lecture. So have a look at these checking questions. I'm kind of assuming you're responsible with your own time and you're the master of your own destiny, right? So I can't crack the whip too hard, but this is me trying to crack the whip. All right. I think that's all of the housekeeping, except one other thing I wanted to mention. With the assignment, I've been saying things like don't change the API. And let me try and explain quickly, maybe with a picture or something, what it means to change. Actually, maybe I'll look at the code. No tricks here, so let's go to a new window. Don't go into solutions. Structures. Okay, let's look at dynamic array. So here's an interface we've given you, an interface, an API, an ADT. Hang on, I'll make it dual to make this easier. Sorry. Okay, so this is what you get given. This is some empty thing. It's basically, here are the functions we want you to be able to support. We want you to be able to support things like string is mostly to help you debug. It's going to convert your dynamic array into some string representation that you can print out. We also want you to be able to get elements inside your array. We want you to be able to set elements. We want to be able to append stuff. We want to be able to prepend stuff, so on. But if you decide that for some reason you want a function that converts everything in your array to be a string that says like hello or something, you can basically do this. Overwrite all with hello, right? Very boring. And then, you know, for thing in array, this isn't real Python, but you get the point. Thing is hello or whatever. You can do that because if you think about what we have, when we implement a grader, an auto grader, it knows the functions we've given you because that's all that it can know. So if you implement other functions, the auto grader can't know that they exist, right? So we can't magically call your special functions. You can call them inside your other methods and they might get called, but we can't say, hey, this student implemented this, overwrite the whole array with dog or whatever thing. We just can't possibly know it exists. So you can do that. You can add to your API. You can extend the API. What we don't want you doing is taking something like prepend and saying, actually, I want to add 10 more arguments here, like thing, int, blah, 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 right? Or whatever. Because if we try and do an auto grader run on this code, the auto grader is going to explode and say that function has the wrong parameters, right? Does that make sense? So you can add functions if you want. If you do try and change the signatures of these functions, you should probably just add a private function with different signatures and call it from these, right? If you really have to. But don't change the interface we gave you, or else the auto grader will blow up and it will be your fault, okay? I hope that makes sense. The other thing, just really quickly, while we're talking about it, if you're not sure that something is banned or not, the kind of thing to think about is, could I do that in C or some other low-level language? So for example, you can get, say you have an array you need to get elements in the array. You can look up array of some index and get the element out, right? You're allowed to do that. C can do that. You can do that too. What we don't want you doing is stuff like saying if thing in list. Because if you say in Python, if thing in list, it looks like a single line. It looks like a single function, returns yes or no. But actually under the hood, Python's going through everything in the list in linear time to find whether or not the thing's in there, right? And so it's hiding a bunch of functionality that you should be implementing yourself. So that's kind of the rule of thumb. Just ask still if you're not sure. But otherwise, hopefully that gives you kind of a temp check. And I put something at the end of the last spec that kind of explains that. Any questions about housekeeping, assignment, etc. before we move on? Yep. Yeah, good question. So the question is, how can Gradescope evaluate my string printout? Because it might be different between students. We don't test that, actually. So another one that people have been getting a bit stuck on is with dynamic list, is it full, right? To me, and we talk about list today, so we'll get to this, if there is any position in that list that could take on an element, it's not full, so return false. Otherwise, return true. However, that's just convenience function for you. We won't be rigorously testing that. However, what we will be doing, the tests kind of look like this to give you an idea. We get dynamic array, x equals dynamic array. We generate 1 million elements. We randomly flip coins, appending, prepending, reversing, blah, blah, blah. We also keep a real list that does the same stuff, and then at the end, we check that the elements are the same in the same order. So things like that is what we're testing, right? So we're trying to see if your data structure is behaving the way we expect it to. That's a great question. Does that help? Yeah. Any others? No, I don't think I see any hands. Wave if you're furiously wave. No? Okay, cool. Let's go. Let's go with the lecture. So today, we're going to have some fun, as always. We're going to talk about... Oh, actually, sorry. One more housekeeping item. This one, back to the doc cam. Suppose it's an exam. Right? Suppose it's the end of your exam. And I ask you a question like this. Can you see that okay? So it says, specify the big omega for this algorithm. And then there's an algorithm there. Are you going to be annoyed at me about a question like this? Who would be kind of annoyed about this question? I would. Now, my greatest fear as a coordinator is sitting there when the exam goes in and waiting for the phone call. Because when you ask a question, the examiner leaves the room and they ring me and they say, hey, some student said on question 1A there's a mistake. Right? My heart stops. And I say, the student's wrong. But sometimes the student's right. So what's wrong with this question? Yep. Yeah, well, there's a couple of things possibly that are wrong with this question. The first is that here we have a case where we run in constant time, right? Sorry, I was going to write of 1, and then I thought that was a bad idea. So if the list happens to be divisible by 2 with no remainder, that thing returns. Otherwise, it goes through and it sums up the elements in the list, right? And this is linear time, I hope you agree. But the problem is, you're going to hit this constant time operation when? In what case? The best case behavior of this algorithm enters this, right? The worst case behavior of this algorithm enters the else and does a linear pass, right? Does the question say anything about which case we're talking about? No, okay? Now, I've told you, if we don't say otherwise, assume worst case, but it's a bit sloppy. So the point is, now, how does this come back to you? If you're making a question on Ripple, I want you to be very precise. I want you to think very carefully about what you're saying. This question is underspecified. If the answers were something like, could be this, or maybe it's this, well, this is true if you're talking about worst case. Oh, sorry, you can't see. Oh, wait, I've taken a photo. Hang on, let me figure this out. Go away. I actually have no idea how to work this thing, so I'm going to use the other one, low-tech solution. And let me put the light on. Well, if I take a photo on this one, we're screwed. So it could be this, if we're talking best case, or it could be the other one if we're talking worst case, but the question doesn't say which case we're talking about, right? So it's a bad question. So please try and specify. Same thing. Can you see this okay? Here's a question. Specify the big O bound for this function, or of this function. 10n cubed plus 3n squared plus log n. Select one of these answers. Which ones are candidates that are correct? What do you think about the function? What's the highest term in the function? Yeah, so is this true? Yeah, is this true? Is this true? Is this true? Which one's the tightest bound?
Titus?
This one, right? So the student probably is asking which one's the tightest bound, but they didn't say so. And again, I told you to assume that. But what happens is if I write a question like this on exams, I get phone calls, right? So if you're writing questions for your colleagues, please try and be conscious about this. We need to be very precise. And you can see, I even told you last week how I made a mistake last year, not being precise enough about a question I asked. So please just try and think about that a little bit as you're going through doing your Ripple questions. Awesome. All right, let's go to sorting again. Okay. Remember that last week we talked about sorting. We learned some cool sorting algorithms. If you've been to the tutes, you've sort of been through them again. Simple ones. Some run slower than others. But what all of these sorting algorithms had in common was that they're comparing keys, right? So for example, I might just change color here. So all of the sorting algorithms we looked at, bloody technology, they do some comparisons, right? So the point is that if we want to say whether element A or B is bigger, we compare.
Yo, my Instagram needs to chill.
compare them. We say which one's bigger, right? So there's always this comparison going on. Examples we had: bubble sort, insertion sort, selection sort. Do you remember what these ones run in? Worst case?
Worst case bubble sort was order and factorial. Insertion sort? Oh, and
N squared, worst
right?
case, right? And then you had merge
N squared. Merge sort.
sort. What's the worst case of merge sort?
And log n.
And log n, merge sort. What about quick sort?
Log n.
N squared, but O of what? N log n what?
N log n. What's it? Estimated.
Expected, right?
Expected.
If we do random pivoting. Okay, so we've seen some sorting algorithms, but all of these in common have this idea of comparison, right? So last week I said something like, hey, you can't do better than merge sort. Now when I'm talking about better here, I'm talking about a comparison model where I'm interested in counting the number of times I have to compare element A and B. Okay, and so last week I said something like, hey, merge sort is as good as you can do in terms of the number of comparisons that must be done to sort some input in the worst case, right? Now I'm going to try and convince you that this is true, and that is that any comparison-based sorting algorithm has to have big omega of n log n comparisons in the worst case. It's lower bound at n log n. You can't do better in the worst case. Of course, you might do better in some other case. Did I show you that? Did we see an algorithm last week that actually could do a pass-through in linear time? It was bubble sort, right? Remember that bubble sort, if the list is already sorted, it compares a pair, a pair, a pair, a pair, and then it's done. And you didn't do anything? That's actually doing a linear number of comparisons. But that's the best case, right? I'm talking about worst case. So you have to do, what I'm claiming here is that you have to do at least n log n comparisons in the worst case. So what we're going to try and do now, and I'm going to mess up the math for sure because I am a bit nervous doing math in front of a big cohort, and most of you are better at math than me. So we'll give this a try. I'm going to try and mount a case about why you have to do at least n log n comparisons. All right. So what we're going to do is try and find, or we're going to try and derive a worst case lower bound. Now, I'm going to diverge from the slides, and that's what's making what I'm about to do a little bit dangerous for me. But it's all in the slides if you're interested. So, and that's why if you can't see the desk, I've got 6 pieces of paper laid out in front of me. So I've been thinking about this all week. All right. So what happens when you compare two elements? What is the output of a comparison? Basically, you can say, is A greater than B? What is the answer? What are the two? I've given it away. What are the two possible answers? True or false, right? So let's build a comparison model. And I'm just going to set some notes here. And I think the reason I'm doing it this way is because last year I found people got a bit hung up on this because I skimmed through it a bit fast. So I think if I kind of slow it down and show you from first principles what's going on, maybe you'll understand a bit better. So in a comparison model, we can compare two elements A, B. I'll always use less than, but you can use any comparator you like. And you're going to actually get some tree that's like this. No and yes, right? Do we agree? And so if I have some other stuff going on underneath with other comparisons that I'm just not going to show, what you'll notice is that the left half of this tree, and let me explain what a leaf is an output, okay? So when we're sorting, we can go down, oh, that's kind of hard to see. Can you see it okay? Yeah, okay. What you do is you go down this tree of comparisons until you get to the bottom. And at the bottom, you've got a leaf. And what a leaf is a configuration of the output, okay? So essentially, if I have this tree with a bunch of stuff going on and I get to a leaf, all the leaves on the left side of this tree have something in common with each other. What is it that they have in common? It's in the top there. Yeah, what is it? A has to be what? Is A less than B? No. So A's come where? Before or after B's? After?
What? Greater.
All this binary comparison is confusing, right? If A is less than B says no, then A has to be greater than B, right?
Yeah.
So that means that all the outputs on this side of the tree are blah, 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 B, blah, 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 A. A has to be on the right of B. I hope you agree, right?
Okay.
Now, all the leaves on this side of the tree obviously are the other way. Blah, 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 A and then B. There are lots of different potential ways they could be next to each other, maybe not. Do you buy what I'm selling here? Do you agree that you're going to have some leaves with A on the left and B on the right and the other way? And that decision was made at the root of this tree, but other decisions can be made at other leaves of the tree. Okay, so we've built a comparison model where we agree, at least you're warming up to the idea, that walking through this tree gives us some path to an output, right? Okay, cool. So what I'd like to point out now is that these clouds obviously have a bunch of other comparisons in them, and I think it's a little bit annoying to draw, so I'll put it on the doc cam again, and let's hope I don't take a photo.
Where do I search myself up? I'll just search Wilson. Study stream. "12 hours study." That's crazy. 12 hours study. Bruh. You're crazy. Maybe I should just put lo-fi music and do my own shit. Yeah, let's do that actually.
So you think you know Wix, but do you really?
Oh, I'm on the wrong one. So hopefully you can see that. So here's one I prepared earlier. You've got 3 elements in a list, right? A, B, and C. And if you have A less than B, no on the left, on the right, at the leaves you can see the orderings that come out from sorting these 3 elements, right? Now, you might start thinking about, well, I've got 1, 2, 3, 4, 5, 6 leaves, right? And that's because my input had 3 elements, okay? So we can generalize this a bit further. I'll leave that up there for a sec, but it's going to be captured in the lecture recording if you want to go back. What I'll do then is let's think about permutation.